So we're going to continue now. This next process, or this next question, has an isothermal process. So before it was polytropic, now it's a different type of process. It's an isothermal process. So that means a process that occurs where the temperature throughout the process does not change. So this will be question 4.2. A piston cylinder device initially contains 1 meter cubed of saturated water liquid at 200 degrees Celsius, which is now expanded isothermally until its quality is 70%. Calculate the final volume and the total work done by this expansion. So a few things to note before we start actually solving this. It's a closed system, so this 1 meter cube doesn't change. I'm sorry, the 1 meter cube can change. The amount of the mass of water in here does not change. Also, if you read the question carefully, it's saturated liquid water at 200 degrees Celsius, which means in the property tables, when we look for this, we know we're at exactly a quality of 0. We're not a compressed liquid, though. We're just at that point where the compressed liquid starts to become a mixture. So we're looking at UF and VF. The sub-F properties are what we're interested in. So also another thing to note, it says here the temperature is 200 degrees Celsius. And as I said, this is, as the question said, really, this is an isothermal process. So that 200 Celsius will not change either. So let's get started then. Let's open up a note. So state 1. Well, the question first asked us to find the final volume. So let's first look at what the initial state is in terms of the volume. Well, we know that V, and I'll put a strike through to show that this is the volume and not the specific volume. No strike through, specific volume. So V at the first state, we're told it is 1 cubic meter. But what's the specific volume and what's the state in general in the first case? So if we go to the property tables for water, here we are. Saturated water pressure. This is the pressure. We want the temperature. Sorry, I missed it. There's the temperature. So we're told we're looking at this line, the 200 degrees Celsius line. And like I said, since this is exactly a saturated liquid, we're interested in the sub-Fs. Sub-F. So not all of these are of interest to us, but just so you know, this is what we're looking at. So if you remember here, just draw it here, in a TV diagram, basically what we're looking at is this point right here, just on the line. So if we continue to add energy, we're going to start moving this way, right? This is the compressed liquid region that I just drew. We're just at the limit between the compressed liquid and the mixture region. And as we do this process, we're told we're going to move at a constant temperature to a 70% quality. So in other words, 0.7 of the way down this line, this horizontal line. We're going from state 1 to state 2. So state 1, that was fully defined by the VF and all that. So if you look here at state 1, clearly our VF is 0.001157 meters cubed per kilogram, right? So let's write that down, 0.001157. And that's meters cubed per kilogram. So if we flip that around to the -1, we'll get the density. And that would give us a density of about 864.3. 864.3 kilograms per meter cubed, but we only have 1 meter cubed. So of course the mass contained here in this system, which isn't changing, is 864.3 kilograms is what we have. And we're going to now put that on the back burner until we figure out what the specific volume is at state 2. So we know that V2 happens, meaning the specific volume happens 70% of the way between VF and VG, right? So we're 70% of the way here. Now V1 equals VF, so we can keep that around for the next calculation, but I'll just get rid of this. What I'll do actually is I'll just go straight for VG. So let's find VG, and then we're going to interpolate 70% of the way between the two. So if we go to VG, we see that VG is 0.12736. So 0.12736 meters cubed per kilogram. Okay, so quality of 70, so X equals 0.7, basically means that our second specific volume minus VF is equal to VG minus VF. And this is what we're trying to find, and these are all known. So if we do the math here, so 0.7 times VG, which is 0.12736 minus 0.001157. And then we add VF, which is V1 and VF are the same, right? Because state 1 is at that saturated liquid state. So we're going to add 0.001157. We'll end up with, so I'll just do this. V2 equals 0.0895. We'll say 0.0895 meters cubed per kilogram. This is our value. This is our value of V2 for the second state. So clearly, now knowing V2 and recalling that the mass we already found is 864.3, we can find the actual, volume at state 2 by multiplying them together. So that should give us 0.0895 times 864.3 equals 77.35 cubic meters. All right, so this is our answer to the first part of the question, which is again asking us to find the volume at the end of the process, but it's also asking us to find the work. So what I'll do is I think I can fit it over here. So remember, again, work is the integral of P dV between states 1 and 2. Now, here's a bit of a trick to this question. So if this were an ideal gas, what we could do is replace P with the ideal gas equation, the MR, because it's isothermal, the temperature, MRT, all of that comes out, and we're just left with 1 over V dV in the integral, which of course is ln of V, and with a definite integral, it becomes ln of V final over V initial. So in other words, the work if this were an ideal gas, could be expressed as MRT ln of VF over V initial. Now, of course, this is not an ideal gas because this isn't a gas. This is only a 70% mixture. It means 30% of this is a liquid. We can't call this an ideal gas. So this here is actually wrong in this case. Again, ideal gas, this is the way to go. This is not an ideal gas. So what can we do with this? We still have to evaluate this integral somehow. Well, if you recall on that little sketch I drew, we're moving horizontally on a line of constant pressure, right? So in the subtext of this question, really, this is also a special case, I'll say, where we have a constant pressure process. Well, that we can solve this integral pretty easily, right? The P comes out. We have dV So it's literally just the pressure, which is constant, times V2 minus, oh, these should be strike throughs, V2 minus V1. That's the work done. Now, pressure, do we know the pressure? Well, yes, it's a constant pressure. And we know from the property tables that the pressure at saturation, which we are at, is 1.5538 megapascals. So if we go here, work equals 1.5538 times 10 to the 6 times V2 minus V1. So 77.35 minus V1, which was given as 1 meter cubed. This will give us the work. So let's just run that through really quick. And dividing by, even divide by a million. So that's 118.63 megajoules, so million joules that we're getting from this. So yeah, that's the answer to this question over here. That's the amount of work that we're doing. You'll note that this is, again, a positive number. And the reason it's positive is because work is being done. So if you remember in the last case, we were compressing from, I believe it was can't remember, but in part B the volume was decreasing, so we had negative work, meaning work was being done to the system. Whereas here we have an expansion from about 1 meter cubed to 77 meters cubed. So this is giving us a positive value, which we expect because we're expanding, we're increasing in volume, we are doing work. It's a positive value. Work is not being done to us, which would be a negative value.